Okay, so at the beginning, I said I cannot be here. This week is fine, but I can't be here Thursday or Friday of next week. We're supposed to have the statics exam 3 on Friday. So I'm figuring out right now whether we're going to either have the exam Wednesday, and if that is a problem for you, come talk to me. I can be very flexible with that because I'm changing it at the last minute. Or hopefully what'll happen is I can get a proctor. I'm focusing my attention on Sue Kasahara because she has trouble saying no to people. And so I'm going to exploit that.
We have it next class. We'll tell her that you said
No, don't tell her. I need, no, go to her with just really sad eyes. Like, I really want to take the final on Friday, but I don't think it's going to work out.
I can do that too.
Okay, so I will let you know on D2L, I don't know, today or tomorrow at the latest. All right, so thrust bearings. This is where you have an object that can rotate. Last time I did it solid. It can be solid or a cylinder pipe like this. And there's a force here that I'll call N. And the thing resisting the rotation is just friction between this tube and the ground. You can think of this 2 different ways. I mean, with journal bearings, you can think of it this way too. Although with journal bearings, more likely what you're going to want to do is figure out what moment needs to be applied to overcome to keep the thing moving with a constant velocity. But this can be moving with a constant velocity, and you can see what couple you need to apply to keep it moving with a constant angular velocity. Or more likely, it's like what couple can you apply before it starts to move? Okay, so if your coefficient of friction is the static coefficient of friction, that's the maximum couple you can apply before this starts to rotate. This is less common, but if this is the kinetic coefficient of friction, what you're calculating is the couple required to keep it rotating with a constant angular velocity. Do you guys know that Sue Kasahara is our school's nominee this year for the Board of Trustees Excellence in Teaching Award? You probably didn't know that because it's hard for me to imagine her being like, I got this award, suck it, bitches.
She's a great teacher, though.
So good.
I wish
The
it was
best.
like that.
Just once a semester. Yeah, it's hard to imagine that. So I'm her PR consultant.
She gives out these like little pins.
Oh, yeah.
Yeah, and like if you get the best score on the, what is it called?
Is it the what part of the Maxwell's equations don't you understand? Is that the pin? She used to hand those out to everyone. Those were funny.
No, it just has just equations on it. But you take the standardized testing.
Oh, yeah.
And then whoever got the best score get a pin.
Oh, okay, yeah.
I have a pin.
Oh, yeah, cool. Yeah, she used to, everybody had these big buttons that were like, there's 4 Maxwell's equations, right?
Yeah.
And it's like, what part of, with the 4 equations there, don't you understand?
Maybe that's what it is. I don't know. I can't remember.
It was funny. Okay.
I remember she was like doing a static electricity lab, and she like contracted a soda can with a PVC pipe, and she called it a really cool party trick because she was like super excited, and she was like saying, "You show this to your friends." I was like, she must be like the sweetest person ever. She thinks this is like the cool party trick.
Yeah. Well, she's married to a physicist too, so her idea of social interactions probably has gotten warped over the years. Okay, so here's the strategy. I told you this last time, and really, you're better off just remembering the strategy and not trying to remember the details. Just work through the details on your own. So first, we're going to... Okay, let me draw the picture. So in this case, there's the part that's in contact with the ground. And we're going to break it up into these infinitesimal rings. The distance from the center of this tube out to the infinitesimal ring is lowercase r. The thickness of the ring is dr. And so the first thing we're going to do is figure out, so the total surface in contact with the ground is taking up that total normal force, right? So how is it split up? Well, it's just split up by areas. So first, we're going to figure out the fraction of, the infinitesimal fraction of that normal force that's acting on that infinitesimal area. We're going to do that just as a fraction of the total area. Then, once we have that, we're going to figure out the friction force on that infinitesimal ring. That's just going to be the coefficient of friction times that infinitesimal normal. Then, since at every location along this ring, that friction force is perpendicular to the line to the center of the circle, we can calculate the infinitesimal moment about the center that's produced by that infinitesimal ring. That's just going to be r times df. And then the last thing is just the moment, the total couple is the integral from the big inner radius, the macroscopic inner radius of that tube to the macroscopic outer radius of that tube, and we're just integrating these expressions for the couple. Okay, if the tube is solid, this is just equal to 0. Okay, so let's go through this calculation. I'm going to just use these values. So I'm going to say the outer radius here is big R outer. The inner radius is big R inner. That won't come up until the end when we need the boundaries of integration. Okay, well, the first step is we're going to recognize that the ratio of the infinitesimal normal force on that ring to the total normal force is the same as the ratio of the infinitesimal area to the total area. Okay, so dn over n is equal to, what's the area of this ring? Stretch it out. The length is 2 pi r. The thickness is dr. And so dA over the total area in contact with the ground is 2 pi little r, because we're doing this for that infinitesimal ring, okay, dr over pi times the quantity r outer squared minus r inner squared. We want dn, that's just the total normal force acting on that infinitesimal ring, so just multiply n to both sides, and you get, you can write this as n over pi r outer squared minus r inner squared times pi. So those pi's cancel out, times r dr. So we got n over r outer squared minus r inner squared times r dr.
Are we missing a factor of 2? Yeah.
Yes. Thank you. Okay, so that's the normal force. Now that we have the normal force, we can figure out the total friction force. So the force of friction is just the coefficient, so 2 pi n over r outer squared minus r inner squared. You can't do this, I know, but I can. I'm going to say, so this is just the coefficient times dn. The moment arm of that friction force is r. So the infinitesimal moment applied by this ring couple is 2 mu normal over r outer squared minus r inner squared times r squared dr. And now finally, just integrate that. The total couple is the integral. The integral of this thing, you can pull out all those constants. So 2 times mu times n divided by r outer squared minus r inner squared times the integral from r inner to r outer of r squared dr. So this is 2 mu n over r outer squared minus r inner squared times r to the third over 3 evaluated from r inner to r outer. And so that is 2 mu normal times r outer squared minus r inner squared. I'm going to pull that 3 out also. So we got a 2 here, a 3 there, and then times, now evaluate this function, r outer to the cubed minus r inner cubed. And now you can get a little bit tricky with that if there is a little trickiness you can use. I believe. So let's see. So this would be, I don't know. Don't worry about that, because you're gonna do this step by step like this. You're not going to use this formula, so that formula can get a little bit simpler, I think, if you factor this, and you can cancel some stuff. But don't worry about that. This is what you're going to do, and you can just put numbers in the whole way, you know. All right, so let's do an example. So let's say that we have a solid object, and let's say that this radius is 0.02 meters, and there's a force down of 500 newtons. And then let's say that you have one like this, applying the same force, a total of 500 newtons. And let's say that our outer is 0.02 and our inner is 0.01. The coefficient of friction is 0.1. And we want to know, so this is a static friction. What's the greatest couple that can be applied without these starting to move? Anybody have any intuition about which of these is going to be higher?
The solid.
I think it's actually, like, you would tend to sort of think the solid, but I think it's going to be the hollow one, because the normal force taken up by that infinitesimal ring is going to be a bigger fraction of the total normal force. Are you with me on that? So we'll see, though. All right, so I'm going to start out. So for part A, we're going to do the solid one. We have our infinitesimal ring. The thickness is dr. The distance from the center to the ring is r. And so the first thing we want to do is calculate the infinitesimal normal force. That over the total normal force is dA over A. And so dN is equal to N over A dA. N is 500. The area of this whole thing is pi times 0.02 squared And then the area of the infinitesimal ring is 2 pi r dr. So we have the pi's cancel. And we have 500 times 2 over 0.02 squared times r dr. Can someone calculate that for me?
Giant numbers, I think.
Well, it's a giant number times,
It's divided by small.
Times this, okay.
yeah,
So it's 2.5.
2.5 what?
Million.
Oh.
6.
2.50 times 10 to the 6 r dr. Okay. That's a big number, but dr is small, so. And now we'll go to the friction force. So d force of friction is the coefficient times dn. So that's 0.1 times 2.50 times 10 to the 6 r dr. So that's 2.50 times 10 to the 5 r dr. Now the couple applied by the friction on that infinitesimal ring is r d force of friction. So that's just 2.50 times 10 to the 5 r squared dr. And so the total couple is the integral from 0 to 0.02. I'll pull out all the constants. 2.5 times 10 to the 5 times r squared dr. So that's 2.5 times 10 to the 5 divided by 3 times r cubed evaluated from 0 to 0.02. And so this total couple is 2.5 times 10 to the 5th. Okay, so that divided by 3, that should be 8.3 repeating times 10 to the 4th. Is that right? Forget you guys then.
You're going too fast.
0.02 cubed. And can you multiply that out?
No. 33.3 repeating.
33.3 repeating Newton meters. Sorry, I think I go fast by accident when I'm like
In the zone.
when I'm like near the limit of my brain power. It's like a self-conscious.
Yeah,
He's
squeeze
just
the
being a
ass out of the
hater.
toothpaste tube.
Yeah.
No, I think he's going faster than me and he's at the limit. I'm like barely keeping up.
Okay, any questions about that? So now we're going to do it again, but for the hollow ring. So you can apply a couple of 33.32 without this thing starting to turn. But if once you hit this, it'll start to turn. Okay, so
I typed in squared, not cubed.
oh,
Oh, it's 0.66 repeating. First one time.
oh, okay. 0.6 repeating. So this is all the same again. This thickness is dr. From the center to the infinitesimal ring is r. The normal force on that infinitesimal ring over the total normal force is equal to the area of that infinitesimal ring divided by the total area. So dN is equal to N over A dA. N is still 500. This time the area of the whole shape is pi times 0.02 squared minus 0.01 squared times 2 pi r dr. And so dN is equal to, cancel the pi's, 2 times 500, so you got 1,000 divided by 0.02 squared minus 0.01 squared times r dr. And can someone calculate that constant?
2.3 times 10 to the 6th.
3.3 repeating times 10 to the 6th r dr. And now the friction force on that infinitesimal ring is the coefficient times the normal force. So that's 0.1 times 3.3 repeating times 10 to the 6th r dr. So that's 3.3 repeating times 10 to the 5th r dr. And now the infinitesimal couple is just r, little r, times dff. And so that is 3.3 repeating times 10 to the 5th times r squared dr. And so then the total couple is 3.3 repeating times 10 to the 5th times the integral from 0.01 to 0.02 of r squared dr. Integrating r squared dr is going to give you r cubed over 3. So the 3 makes, dividing this by 3 gives you 1.1 repeating times 10 to the 5th times 0.02 to the 3rd minus 0.01 to the 3rd. And what do you get for this?
I got 0.77.
Okay, so not that much bigger, but a little bigger. Is it 7 repeating?
Yeah.
Newton meters. So basically, so intuitively, why does it work that the hollow one can deal with a bigger moment than the solid one? If you think about the stuff that's missing in the hollow one, that's all the stuff that has a really small radius for the moment, you know? a small moment arm for the couple. And so all the stuff that has a big moment arm is taking up all of the force, and so that's why
So
it's
the thinner
extra
the
moment.
Wall,
What?
the thinner the wall, the more.
Yeah, the thinner the wall, the bigger that moment should be, it seems to me.
Is there a limit? Like, yeah, as you go thinner.
No, the biggest would be an infinitesimal ring.
Well, if you just smash, so.
Don't even start with that.
It's crushed. And then
Like a tin can. Yeah. Yeah, infinitesimal would be the biggest, but yeah, an infinitesimal wall doesn't hold up to compressive forces very well.
How about the opposite, or the outside diameter just shrinks and you have the same force applied?
Let's see if we can tell that from the. So from this formula, the R inners would be 0. It looks like as R outer goes down, the couple goes down also. Because you have an R outer cubed on top and an R, you know, if the R inners go away, there's 0. Then you just have 2/3 mu normal times R outer. So it's linear with R outer. Any other questions about that?
So you only get more friction if you're thinning the wall towards outer instead of towards inner.
Correct. That's right. I think it's just all a matter of, are you keeping stuff with big moment arms or stuff with small moment arms?
Yeah.
Okay, well, let's stop there. And next time I'll do just a combination of a, let me see if I can draw this picture. So let's say that you have an axle like this with a flange. And it's put into a bearing like this. So there are 2 places where you're going to have friction. You're going to have journal bearing friction there and there, if you can picture that. And then you're going to have thrust bearing friction here and on the hidden side of that flange. Okay, so we'll do that next time. And we have to go upstairs.